Ho, ho, ho! Goosebumps galore! Good morning, good afternoon, good evening. We are back and better than ever. Boys and girls, the greatest day of your lives. We are going to talk about and understand the fundamental theorem of calculus. Sir Isaac Newton to the left and Gottfried Wilhelm Leibniz showed the link between differential calculus, taking the derivative, and the definite integral or limit of an area sum, Riemann sums, we saw in the previous section, or in section A, I should say. This link between differential calculus and the definite integral is called the fundamental theorem of calculus. Ooh, I can't wait to get to it. The beauty of this theorem is that it enables us to evaluate complicated summations, Riemann sums. We have already observed that. Now, this is when we were doing our exploration of the area under the curve. And what we observed was to find this particular area here, or the area under a curve and above the x-axis from 2 points along the x-axis, all we have to do is take the integral from a to b of f of x dx. And we were doing that using Riemann sums. We were using rectangles and hundreds of rectangles to estimate it, and then we had limits come in there. But now we are going to be able to do it so easily and simply. But to get you there, I need you to first consider a few examples. And here we go. Consider the constant function f of x equals 5. And here it is graphed for you, right here. So this is intersecting the y-axis. Oops, that was weird. At 5, right there. That's the point 5, f of x equals 5. And we wish to find an area function, which will give the area under the function between x equals a and some other value of x, which we shall now call t. Okay? Well, we know that the area function, a of t, just from what we said before, let's just take a quick look back here. From the area under curve is given from a to b of the function f of x, whatever that function may be. Where our function here is 5. So a of t is equal to the integral from a to t of 5 dx. Yes? Okay. It's also equal to the shaded area of the graph, the shaded area, yes? Because that's what we discovered, explored, proved that an integral is. It gives us the area under the curve. Okay, so it's equal to the shaded area. Well, we know that this shaded area is equal to t minus a, that's that length right here, times the width or the height, however you want to think of it. Well, this height is 5, so it's equal to t minus a multiplied by 5, which I can easily write as 5t minus 5a. So I'm going to say that a of t, the area under the curve here, is equal to 5t minus 5a. Now we can write this in the form of capital F of t minus f of a, and where f of t is equal to 5t. There we go, it's equal to 5t. Well, equivalently, or which is equivalent to, since this is the x-axis, it's equivalent to f of x is equal to 5x. Now if I take capital F of x and I take its derivative, I get 5. I get 5. So f of x, capital F of x, is the antiderivative of f of x, right? because f of x was 5, and the antiderivative is 5x right here. In other words, if I take the derivative of 5x, I get 5. That makes it the antiderivative of 5. Okay, so put that in your back pocket. Let's try another one. Let's consider f of x equal to x. Okay, so the area, and it's the same scenario from a to t is some value along the x-axis. The area is equal to the integral from a to t of f of x, which is x, dx. Yes? Okay, which is also equal to the area under the curve, the shaded area here, which I'm not going to write. Well, this is a trapezoid, and the area of a trapezoid is equal to the sum of the bases. Let's just call them P and Q because there's A and B's here already. I don't want to confuse you. The sum of the length of the bases. Well, actually, we have them right here, A and T. So A plus T over 2 multiplied by the height. Okay. Well, this is base 1 and this is base 2 of the trapezoid, and the height is T minus A. Okay. Well, if I work this out, I'm going to multiply this out here, and I get A plus, oh, that's a T, that's not a 2, A plus T, sorry about that. Let me erase that and make it prettier. A plus T, base 1 plus base 2, over 2 times T minus A. So if I multiply that, A plus T times T minus A, I get, or I end up with T squared minus A squared over 2, just a little bit of algebra, which is equal to 1/2 T squared minus 1/2 A squared, which I can write as f of t, capital F of t, minus capital F of A. F of A is 1/2 A squared. We're not talking about that one. So where f of t is equal to 1/2 t squared, which is equivalent to, I'm abbreviating, f of x equal to 1/2 x squared. Well, guess what happens when I take the derivative of capital F of x? The derivative of capital F of x is equal to 1/2, that is equal to x, isn't it? So once again, f of x, capital F of x, is the antiderivative, I'm going to abbreviate for time's sake, of f of x. And I'll write those functions out in front of you for you. Remember, f of x is equal to x. And capital F of x is equal to 1/2 x squared. It is the antiderivative. The antiderivative. One last little example here. Same scenario from a to t, but this time my function is 2x plus 3. So the area of that is going to be given by the integral from a to t of the function 2x minus 3 dx, which is also equal to the shaded area again. Now this algebra gets a little bit messier. Okay, so that's the sum of the two bases divided by 2. Then the sum of the two bases is 2t plus 3 and plus 2a plus 3. So 2t plus 3 plus 2a plus 3, all divided by 2. So that's the sum of the two bases divided by 2, multiplied by the height, which is t minus a. Okay, so 2t plus 3 plus 2a plus 3 is equal to 2t plus 2a plus 6 all over 2 times t minus a. Oh, they're all divisible by 2. That's helpful. Equals t plus a plus 6 times t minus a. And I will bore you with the details, but you could use the distributive property and multiply all of this out, and you have some cancellations, and you end up with t squared minus, not minus, sorry, plus 3t minus 2a squared. Okay, 2a squared, which we can write as capital F of t minus f of a, where f of t is equal to t squared plus 3t. Okay, which is equivalent to, since t is along the x-axis, f of x equal to x squared plus 3x. Okay? I don't know why this is 2x minus 3 up here. It should be 2x plus 3. I think I forgot to write the plus. This is the function 2x plus 3. And if I take the derivative of it, capital F prime of x, I get 2x plus 3. And again, I'm not going to write it out again. This shows that capital F of x is the antiderivative of f of x. F of x is equal to 2x plus 3. Its antiderivative is x squared plus 3x because when I take its derivative, I end up with 2x plus 3. Okay? So hopefully you're getting what's happening here, and that is this. The integral from a to t of f of x dx is equal to cap f of t minus f of a, where f prime of x equals f of x. In other words, here is the upshot. F of x is, capital F of x, is the antiderivative of f of x. Now, those were just, that's sort of an informal example as to why the fundamental of calculus is what it is. If you read through the formal proof in your textbook for why the above is true for all functions, okay, I want you to do that. This beautiful formal proof gives us, drum roll please, the fundamental theorem of calculus, the greatest discovery of the human mind ever. And it says the fundamental theorem of calculus. Suppose f is a continuous function on AB. If g of x equals the integral from a to x of f of t dt, then g prime of x equals f of x. That's part one. Part two is what we will be working with, and that is the integral from a to b of f of x dx is equal to f of b minus f of a, capital, notice the difference, where f is any antiderivative of f. Cap f is any antiderivative of f. That is, the derivative of cap f equals the function or that is the integrand in the derivative. Okay, so the upshot is to find the integral, all we have to do is find the antiderivative of the function. Get up off the floor because I know your mind has been blown. Part two coming up.